Hello everyone. In the previous class, we have discussed about the concatenation operator, replication operator, and conditional operator, and we have seen few examples along with the operator precedence. And also we have discussed the programming examples using data flow modeling. That is 4:1 multiplexer. We have discussed using two methods. One is using logic equation and another one is using conditional operator. In today's class, we are going to discuss the 4-bit full adder. So in the previous sections or in the classes, we have discussed this 4-bit full adder using gate level modeling. That is, a 4-bit full adder was designed by using the gates, and we have used the logic diagram for that purpose to write the program in a gate level modeling. But in this type, that is, this is a data flow modeling, so we are going to write the data flow description for the 4-bit full adder, again with two different methods. One is with a plus and concatenation operator, another one is with a carry look ahead adder, 4-bit carry look ahead adder. So 4-bit full adder, we are going to discuss again two methods here. So in the previous case, to design a 4-bit full adder, first we have done was describing a 1-bit full adder. To describe the 4-bit full adder, first we have designed 1-bit full adder, then we have built a 4-bit ripple carry adder, 4-bit full ripple carry adder. So here we again going to illustrate the two different methods. The first one is on your slide, that is method 1 by using the data flow operators. Here we are going to use the data flow statement by using the two different operators, that is plus and the concatenation operator. So the declaration part will be same in any type of modeling, whether it is data flow modeling, whether it is gate level modeling, or it may be a behavioral modeling. So here in the data flow modeling, again we are going to declare the module name is full add 4. The ports are sum, cout, a comma b comma scene, and we can declare the ports. So output port is sum is of 4-bit, that's why it is a vector 3 down to 0 sum, and cout is only a scalar one, that's why output cout. Then we have two inputs a and b, both are of 4 bits, so it is a vector, so input 3 down to 0 a comma b, and the one more input is the scene, it is a scalar one, it is 1 bit, so input scene. Now only thing is you need to do is by for writing the 4-bit full adder is first calculate the size of the output. So our output size is going to be sum and cout. So cout will be more significant bit and sum is 4 bits, so total 5 bits. So assign in a curly bracket cout comma sum, so both are going to be cout is 1 bit and sum is 4 bit, both are concatenated here, is equal to a plus b plus scene. So a is 4 bit, b is 4 bit, and scene is 1 bit. So all these are added and result will be a 5 bit. So this is what the program using data flow modeling using operators finally end the module. Now the second method we are going to discuss is the carry look ahead adder. So you might have come across this carry look ahead adder in digital electronics subject in the 3rd semester. So as we know that there is a disadvantage of ripple carry adder, that is it is having the limiting factor, that is nothing but the time, because from the one block to another block the carry is going to be propagated, so during this the time will be wasted. So as the number of blocks increases, the time will more and more time is going to be consumed. That's why without the propagation we can able to design the adder, so which is nothing but the carry look ahead adder. So here the propagation time of the carry is eliminated here, that's why it is the fast carry adder. So the carry look ahead adder solves this problem by calculating the carry signal in advance. So in this type of adder, that is carry look ahead adder, it is going to calculate the carry signals in advance based on the input signals. So that's why the result is reduced carry propagation time. That is how it is going to be a faster adder. So to be able to understand how the carry look ahead adder works, we have to manipulate the Boolean expression dealing with the full adder. So we have a Boolean expression for full adder. So we are going to manipulate it by taking two different signals, that is the propagate signal and the generate signal. Propagate signal is denoted as P and the generate signal is denoted as G in a full adder. So recall this all the things from the third semester subject digital electronics. So here this is the block diagram of the carry look ahead adder. This is not required here for writing the carry look ahead adder. If you want to write the program using gate level modeling, then this block diagram is required, but still I am displaying this block diagram of a carry look ahead adder. Observe here there are 4 blocks, all are 1-bit full adders. So all are applied with the inputs A0, B0, A1, B1, A2, B2 and A3, B3. And observe here for the first full adder block, a C0, or in the program it is taken as Cin. So Cin or C0 both are same here. So C0 is applied to the full adder and the same input is also applied to the 4-bit carry look ahead adder generator. Now the output of this one will be S0, that is sum 0, that is first block. There are 2 more outputs, that is nothing but P0 and G0. So that is nothing but a propagate signal and the generate signal. So these are the output signals of the 1-bit full adder. Similarly, observe there the C1 is not propagated from the first adder to the second adder. So C1 is calculated here in advance. That's why it is not propagated from the first 1-bit full adder to the second 1-bit full adder. Similarly, all the blocks you can observe there is no carry propagated from the previous block to the next block. That is how the propagation of a carry signal is eliminated. The time is eliminated or reduced. So like this, all the blocks, all the full adder blocks generate P0, C0, P1, C1, P2, C2 and P3, C3. And they are going to produce the output S0, S1, S2 and S3. These are some signals. And finally C4 is the carry output. Cout is nothing but C4 here. So this is what the carry look ahead adder block diagram. Now we are going to see the what is propagate signal and what is generate signal. So observe here P, propagate signal, is nothing but A XOR B. Take a half adder. In a half adder we have 2 equations for sum and carry. Sum is equal to A XOR B and carry is equal to A and P. So same is used here for a propagate signal and generate signal respectively. So P is nothing but a propagate signal, I is the suffix here, Pi is equal to Ai XOR Bi, whereas generate signal G is equal to Ai and Bi. Notice that both propagate and generate signal depends on the input bits and thus that will be valid after 1 gate delay. So we are going to convert this propagate and generate signal into sum and carry output. So as shown in the slide. So sum output S is equal to P XOR Ci minus 1. That is Si is equal to Pi XOR Ci minus 1. That means if I is 1, then S1 is equal to P1 XOR C0 or Cin. Like this we are going to calculate. Then next stage carry, that is Ci plus 1 or C out it is. Ci plus 1 is equal to Gi plus Pi into Ci. So these are the new equations or new expressions which are used here. So these equations shows that the carry signal will be generated in two cases. So observe there, if both the bits A and B are 1. So as we know the addition of two ones, if 1 plus 1 brings the carry, 1 plus 1 is sum is 0, carry is 1. So a carry is generated when both A signal as well as B signal is 1. Then there is one more possibility, if either A or B is 1 and the carry input is 1. Now if either of the A input or B input is already 1 and another one is 0 or 1, and along with that if a carry is 1, carry input is 1, then also the output carry is going to be 1. So based on this you can apply those equations to calculate the C1, C2, C3 and C4. Now C1 is equal to G0 plus P0 into Cin. Observe the previous equation. Ci plus 1 is equal to Gi plus Pi into Ci. So based on this equation, C1 is equal to G0 plus P0 into Cin. Now C2 equal to G1 plus P1 into C1. Just increase the index. C2 is equal to G1 plus P1 into P1 and C1. Now already we have calculated the C1. So substitute the value of C1. C1 value is G0 plus P0 into C1. Cin. That's why the equation becomes G1 plus P1 into G0 plus P1 P0 Cin. This is equation number 2. Now compute the C3 equation. C3 is equal to G2 plus P2 into C2. Now substitute the value of C2. Already C2 is calculated. Substituting the value of C2, you will get C3 is equal to G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 Cin. This is the equation number 3. Then finally calculate C4. C4 is G3 plus P3 into C3. So calculate, substitute the value of C3. You will get C4 as C4 equal to G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 into Cin. This is equation number 4. So using these equations, now you can write the full adder program, 4-bit full adder program using carry look ahead adder method. Now the declaration part is same. Full add for, list the input and output, sum C out A comma B comma Cin, then declare the inputs and outputs. Output is sum, 3 down to 0 it is. Output, one more output, scalar output which is C out, then vector inputs 3 down to 0 A comma B and the scalar input Cin. Now we have a internal wires. Observe the block diagram again. We have a wires there. You have to declare wires here. Wires are P0 G0, P1 G1, P2 G2 and P3 G3 along with C4, C3, C2 and C1. These are the internal wires that are required. Now write the program. Whatever the equations that we have used in the previous slide, same thing is just convert it into a Verilog HDL description. So assign is the keyword used in data flow modeling. So assign P0 is equal to A of 0 XOR B of 0, comma P1 is equal to A of 1 XOR B of 1, P2 equal to A of 2 XOR B of 2 and P3 equal to A of 3 XOR B of 3. Then termination sign. Observe here all the values of P0, P1, P2 and P3 are separated by comma. Then finally one termination symbol is there, that is semicolon. So only one assign, for one assign one termination signal. Now compute the G, that is generate signal for each stage. Now again assign G0 is equal to, just convert those equation into this Verilog HDL form. G0 is equal to A of 0 and B of 0. So dot means it is an AND operation. So use the operator here. a of 0 and b of 0 comma g1 is equal to a of 1 and b of 1, g2 equal to a of 2 and b of 2, and g3 equal to a of 3 and b of 3, termination sign. Now finally compute the carry signal, compute the carry for each stage. Notice that here Cin is equivalent to C0 in the arithmetic equation for the carry look ahead adder. We have used C0 in block diagram. C0 is same as Cin here. So assign C1 is equal to G0 or P0 and Cin, comma C2 equal to, like this. Just write the AND signal and OR signal. Put the particular expression in bracket, and whatever the expressions that we have computed, just transfer it into Verilog HDL form as shown in the slide. Then finally compute the sum. So assign sum of 0 is equal to P0 XOR Cin. Sum of 1 is equal to P1 XOR C1, comma sum of 2 is equal to P2 XOR C2, and sum of 3 is equal to P3 XOR C3. Now finally you might have observed the block diagram. Output is nothing but C4. C4 is, and we have declared the output single carry output as C out. That's why you need to assign the carry output C4 to C out. That's why assign C out is equal to C4. Now end the module. This is how the carry look ahead adder program using data flow modeling is designed. Thank you for watching the video.